right. Hello, everyone. We are going to pick up with our lecture in ionic compounds. And just to kind of remind you where we left off in this lecture, we finished here talking about the main groups, like main groups 1, 2, 6, and 7, and kind of reminding ourselves what kind of ions, cations, or anions they would form. And then we talked about transition metals. And we said transition metals all have 2 valence electrons, but we said sometimes they're not as predictable as main group elements, meaning some of these transition metals I pointed out can form like a +2 and a +3, or even a +4, okay? And so some of them, they'll lose their valence electrons, but sometimes they will then lose additional electrons, is what we discussed in class. So they'll form multiple cations with unique charges, and that's kind of where we paused this lecture. So I'm going to pick up by just looking at this next slide. I'm going to keep talking about transition metals, but notice that the title of this slide is Elements that Form Ions with Predictable Charges, okay? Now, most of the ones highlighted here on this periodic table are main group elements. You see several of the main group 1 and 2 elements, again, always forming a +1 or a +2 cation. You see aluminum here always forms a +3. And then several of our nonmetals, such as nitrogen, oxygen, sulfur, these over here in main groups 5 and 6, these always form anions with predictable charges, and then your halogens in main group 7 will always form anions with a -1 charge. So all these are the main group elements we've kind of discussed, but I want to focus on these transition metals right here. And then you see some of these transition metals in red, some of them in blue. So I'm going to talk about the ones in red for just a second. These are common ions with more than 1 possible charge, okay? So that's what I mentioned on the previous slide. So some of these can form different cations with different charges. And to indicate this, because we're going to spend, I don't know if I'll get to it in this video or maybe the next one, we're going to spend some time learning how to name compounds. And so I want to introduce this idea about Roman numerals, because if I'm talking about let's just say I'm talking about iron. Iron here is Fe. And if I'm talking about an iron cation, if I just say the iron cation, you aren't going to know which one I mean until I tell you, oh, the iron +2 cation or the iron +3 cation. So we use Roman numerals for transition metals that can form multiple charges. We use Roman numerals to indicate which cation we're talking about. And what the exact charge on that cation is. So for example, if I wanted to differentiate between the iron 2 and the iron 3 cation, I would say Fe with a Roman numeral 3 or Fe with a Roman numeral 2, okay? You could say the iron 3, I mean, if you wanted to, let me skip this over. And the iron 3 ion, you could say the iron 2 ion, okay? You could even write out the word depending on what the question was asking you for. Iron 3 like this, or iron 2. Okay, so that's why we use Roman numerals. And they're really only necessary for the transition metals that form these multiple charges, right? Look at the ones in blue. That's down here. Oh, I probably should mention this before I get to the ones in blue. Hg. Hg is mercury, and you notice there's subscript 2 on mercury with a +2 charge. And I just wanted to remind you, or I just want to let you know, it's not a typo. Each mercury atom has a +1 charge, and it just so happens that there are 2 mercury cations bound together there. It's a very unique cation. And so this ion is sometimes called mercury 1, or traditionally the mercurious ion, as opposed to this mercury cation, which is just one individual atom with a +2 charge on it. Here, this one is 2 individual mercury cations, each one with a +1, so they add up to a +2 overall. But that's kind of inconspicuous, right? And on exams, I really don't like to drill students on things that are too inconspicuous. But in case you noticed that, I did want to explain that, okay? All right, now let's talk about the ones, the transition metals in blue here. That's like your Sc, Y, La, over here, silver, zinc, those, okay? In blue, these are other transition metals that invariably have 1 charge, only 1. And so let's talk about Ag, silver. Because silver is only ever a +1, When I say the silver cation, if you know that it's only going to form one charge, we don't have to differentiate because there's not another cation to differentiate between. So we would just say the silver cation. We wouldn't have to write. It would be redundant to say Ag1, okay, because it only ever forms a +1 cation. So it's okay to omit the Roman numerals there. You don't have to include those, but you have to know which ones you're talking about, okay? So you'd have to memorize those. Sometimes I tell people, as a rule of thumb, when you're talking about transition metals, it is safe to always put the Roman numerals. You'll never go wrong by indicating what the charge is on your ion with a Roman numeral. Just for the transition metals, though, not for main group cations. Okay, so next I want to do this practice problem. It's just the next slide down from this slide, and basically we're just going to start practicing writing the symbols for ions that are formed in the following processes. So this is going to give you practice with writing out the symbols for cations or anions. So if you're not sure what a cation or an ani is or can't remember, pause this, go review that really quick. But let's just start with A right here. This is the gain of 2 electrons by selenium, Se. And I made a note of, I mentioned this in lecture on Tuesday of this week, that a lot of times when people read this word gain, they'll think, oh, it's automatically, the charge is going to be positive, whatever it is, it's going to be positive because we're gaining. And so that means plus. But remember that electrons are negatively charged. Okay, so if we're gaining electrons, we're gaining negative charge. Now, selenium, I think I have a periodic table down below. So let's find Se. So Se is right here. It's in main group 6. And it has 34 protons. That's the atomic number there. So if we've got 34 protons in a neutral element, we would also have 34 electrons. Okay, so 34 positives and 34 negatives. That means we got a neutral atom. But if we've gained 2 electrons, that means we got +2 more here. So instead of 34, I should write the negative charge with that. We've gained 2 electrons. Instead of 34 overall, we have 36 electrons now. Okay, now when you add those two numbers up, a positive 34 and a negative 36, you should get a -2 overall. So the way we would write that ion is Se with a -2 charge on it. Okay, so that would be an anion. All right, and remember, we defined an anion is an atom that has gained electrons. That is the definition of an anion. So your anion should, those will always have negative charges. Okay, B, the loss of 2 electrons by barium. Okay, so if we're losing electrons, we're giving away negative charge. You can think of it like that. And let's go see where barium is on the periodic table. It's right here, row 6, main group 2. And it has atomic number 56, which means in a natural element, barium would have 56 protons and 56 electrons. But it has lost 2 electrons. So if it had 56 electrons, but it lost 2 of them, now it would have 54 electrons total. So when you add these numbers up, you would get a +2 overall. Okay, so the ion here, the way you'd write the symbol for the ion is you'd write barium, and then you'd write a little +2 as a superscript up here. Okay, let's do C, the gain of 1 electron by bromine. Okay, bromine is a halogen, so main group 7, and it's actually right next to selenium, so atomic number 35, meaning regular old bromine has 35 protons and 35 electrons, negative charges, but it gained an electron. So now we've added 1 more electron here. So total we should have 36 electrons. Okay, and when you look at the difference between the number of protons and electrons, you have 1 extra electron, and so we recognize that by writing bromine with a negative. You could just write the negative, or you could write a -1, and that's how you would write the symbol for bromine there. So you've got selenium would become an anion, barium would be a cation, and then bromine would be another anion when you gain electrons. So that's that practice problem. I think I have one more after this slide. Okay, this one says, based on the trend in ionization energies. Okay, so maybe you need to go review that. We drew a periodic table and drew those trends out. How would you expect the ionization energies for rubidium and cesium, Rb and Cs, to compare with other members of the 1A group? Now remember, A here denotes that it's a main group. So this is talking about main group number 1, which is the alkali metals. So we need to go find where those are, whoops, on the periodic table, and see where rubidium and cesium are. All right. So I'm actually going to kind of mark this group off. This is main group 1, right? Right here. So you see that rubidium and cesium are right here on row 5 and 6. So they're pretty far down the periodic table when it comes to what row they're on. And if you remember, the trend in ionization energy said that as you go down the periodic table, ionization energy decreases. Okay, as you go down the periodic table, ionization energy decreases. And if you don't remember what ionization energy is, it's the energy required for an atom to give up an electron. Okay, now remember that main group 1 elements, they all like to give up electrons. That's a pretty easy thing for them to do. That's not a hard task because they become more stable when they do that. When they give up their 1 valence electron. So as you go down the periodic table, ionization energy decreases. So what we would expect for rubidium and cesium is that their ionization energy, I mean, you could write this a few different ways, but would essentially be lower. Okay, or smaller, or whatever you're going to say, than other elements, higher up. Okay, so that's that question. And I actually think I'll use the rest of this slide. At this point, I'll make another video for the writing and all the rules with writing the names of cations and anions and compounds. But at this point in the lecture, what should you have a good grip on when it comes to ions and ionic compounds? And just chapter 3 in general. We can make a short list here. I think the first one is you need to know what an ion is and why it's important. Okay, so ions. All right, how do you differentiate between cations and anions? Can't write. And then you need to know why they are important. We talked about several different biological roles they play. We gave several examples. So that you need to know the trends, and I'm going to abbreviate these terms: ionization energy and electron affinity. Okay, so know what those terms mean, what they are. There's energy associated, an energy transfer associated with both of these, and then their trend on the periodic table. Also atomic radii, which was from chapter 2. Okay, but those are the 3 trends you'll need to know for exam 1. You need to know the octet rule. All right, and then the octet rule only applies to main group elements. Okay, so why is the octet rule useful? How do we use it? Well, it allows us to predict whether, I'm going to abbreviate, main group elements gain or lose valence electrons. Okay, it allows us to predict whether main group elements are going to give away electrons or receive electrons to fulfill or fill up their 8, their octet. And when we know what they're going to do, whether they're going to gain or lose, and how many they're going to gain or lose to have a full outer shell, we can know what the charges are. So on the cation, the resulting cation or anion. So it allows us to predict charges on main group cations and anions. Okay, you can know whether something's going to be a +1 or a +2 or a -2 if you know the octet rule. All right. And then what else? Transition metals was another big thing. Okay, transition metals. So what about transition metals? You need to know how many valence electrons they have. You need to know how we talked about that some transition metals can form multiple kinds of cations, and how we use Roman numerals to differentiate between those. I think that might be about it. Some transition metals only form cations with one particular charge. So I'm going to pause this, and then I'll pick up with starting to name things, writing the names of ions first, and then we'll get into